Board now. And so pounds to grams, we're just going to use that conversion factor there, 453.6 grams per pound. Grams to moles, we're going to use the molar mass. Mole to mole, we'll just use the balanced chemical equation. Moles to grams, we'll use the molar mass, CO2, and then grams to pounds, we'll just use this 453.6. And so we're just going to use conversion factors, string them together, and we'll get it. And so what did you start off with, Nordito? Tell me.
453.6 grams of CH4.
Okay, so you could skip a step. I'm not going to skip a step. I'm just going to start off with 1 pound of methane. And then convert that into grams, 453.6 grams per pound. So that gives me 453.6 grams of methane. Then what did you do?
And 1 mole of CH4 over 16.33 grams.
16 point what? 33? 16.33. Well, the reason I have these numbers is because I like, when you have simple numbers, you can do it in your head sometimes. And so 1 carbon is 1201. 5 hydrogens would be 505. So 1201 plus 505, or 405, 4 hydrogens, sorry, 404. So 1201 plus 404 gives me 1605. So I would have gotten 16.05 grams of methane rather than 1633. And so the grams of methane cancel. That leaves me with moles of methane. From moles of methane, I want to go to, And so what was your mole ratio?
1 mole of CO2 and 1 mole of methane.
Yeah, good. That's right. It's a 1-to-1 mole ratio. And it's a 1-to-1, you're thinking I'm multiplying by 1, but it's important because otherwise the units don't cancel. You might be tempted to skip this, but you shouldn't, because you got to make sure everything cancels in dimensional analysis. And then what?
44.01 grams of CO2 over 1 mole of CO2.
Yeah. Right, 2 oxygens gives me 32.00 plus a carbon gives me 44.01. So this is the same molar mass I would have gotten here. And then finally, we don't want grams, we want pounds. So 453.6 grams per pound. That should give us pounds of CO2. So let's go ahead and calculate it. I'm going to skip, because we're multiplying by 453.6 and dividing by 453.6, so I'm going to cancel those out. And so I'm just going to take 4401 divided by 1605, 2.742. 2.742. 0. Now, how many sig figs am I allowed? Well, it depends on what I treat this as. If I treat this as 1 sig fig, then I'm only allowed 1 sig fig here. If I'm only allowed 1 sig fig, then this would round up to 3 pounds. So for every pound of methane I burn, I get 3 pounds of carbon dioxide. But the other way of looking at the 1 pound is I could say this: in exactly 1 pound of methane, approximately how many pounds of CO2 will I get? And then if that's the case, I'll call this exact. And in fact, I'm just going to assume that this is exact. I'm talking exactly 1 pound. Then I got 4 sig figs, 4 sig figs, infinite 4 sig figs, 4 sig figs. So I'm allowed 4 sig figs in my final answer if I say that's exact. And so if I burn exactly 1 pound of methane, I'm going to get 2.742 pounds of CO2 produced. Even though they form in a 1-to-1 ratio, CO2 is just a lot heavier. Methane's 16 grams, CO2 is 44 grams. So CO2 just weighs a lot more. That's why we end up with almost 3 times as much CO2 as we input in methane. When we burn this in air, and in air, oxygen is plentiful in air. Since oxygen is plentiful in air, we don't have to worry about the oxygen. There's plenty of oxygen, so we say there's excess oxygen. You know, as long as you adjust the burner correctly and everything, then it should burn completely. But you know, that's because we're here. However, if you have, let's say you're burning methane in an enclosed container, then there could be a limited amount of air or a limited amount of oxygen. And so if you're on a submarine and you're burning methane, then you got to worry. You know, if you're on a submarine, you're going to be using up oxygen. You don't want to use it all up. And so, worry about that. Which brings us to the next type of example. In this case, we didn't have to worry. Whenever we're just given one reactant, we assume all the others are in excess. That is, there's enough of the other reactants to complete the reaction. However, sometimes we're given more than one reactant. And so let's say if I had this, we're going to do a combustion, but in this case, I'm going to take 115 grams of methane plus, I'm going to go with 150 grams of oxygen. And the question is, if I react this mixture together, how many grams of CO2 will I get? Well, do I have enough oxygen? Maybe, maybe not. Maybe not. You know? Maybe yes. I could estimate how much oxygen I need based on the balanced chemical equations. I mean, the balanced chemical equation was this: CH4 plus 2 oxygens. I need 2 oxygens for every CH4. So does that mean if I have 150 grams of methane, I need 230 grams of oxygen? I need twice as much oxygen. Is that right? It actually isn't quite right. This is what it is. How much does a methane weigh? 16 grams. How much does an oxygen weigh? Well, an O2, each oxygen atom weighs 16. We have 2 of them, so it's 32. So an oxygen molecule weighs 32, and then we have 2 oxygen molecules, that's 64. So for every 16 grams of methane, I need 64 grams of oxygen. Do I have it? Does it look like I have enough oxygen? Yeah. Sometimes we could see it, sometimes we can't. We don't have to see it in this case because we have a special technique. Whenever more than one reactant, whenever the amount of more than one reactant, or in other words, when multiple reactant amounts are given, then this is what we classify as a limiting reactant or limiting reagent problem. That is, one of these reactants will limit how much reaction can take place. You know, maybe I'll completely combust it, maybe I won't. For limiting reactant problems, or limiting reagent problems, reactant, reagent, same thing, we use the smaller amount method. Okay, it's this, use the smaller amount of product method. the smaller amount of product method just does this. We're going to calculate the yield of CO2, you know, from methane. And so the first part is yield of CO2 from 115 grams of methane. So what we're going to do is we're just going to assume we have plenty of oxygen. We're going to burn all this 115 grams of methane and see how much CO2 is produced. So we do that stoichiometrically. We're going to go grams to moles, moles to moles, moles to grams. So grams of methane to moles of methane. So a mole of methane weighs 16.05 grams. So we go grams to moles, then moles to moles. And so we're going to go from moles of methane to moles of CO2. It's a 1-to-1 mole ratio. So 1 mole of CO2 for every 1 mole of methane. So grams to moles, moles to moles, moles to grams. 44.01 grams of CO2 for every mole of CO2. And so this is 115 divided by 1605 times 44.01. 315.3. 315.3 grams of CO2. So if I could burn all 115 grams of methane, I'm going to form about 3 times as much CO2. Okay, part B, what we're going to do is we're going to calculate the yield of CO2 from 150 grams of O2. And so if I use up all of my oxygen, how much CO2 should form? So we'll go with 150. I'm going to call it 3 sig figs here, 150 grams of O2. So we're going to go grams to moles. So 1 mole of O2 is going to weigh 32.00 grams. Each oxygen being 16. Grams to moles, moles to moles. This is going to be 1 mole of CO2 for every 2 moles of O2. And then moles to grams. So 44.01 grams of CO2 per mole of CO2. All right, so let's see. Here, it's going to be 150 divided by 32 divided by 2 times 44.01. 103.1. So then we compare the amounts of product. If I burn all the methane, I'm going to form 315.3 grams. If I use up all the O2, I'm only going to produce 103.1. So what's going to happen is this. Once I use up all the O2, there's no more O2 to combust the methane, so the reaction stops. And so the smaller amount's going to dictate the. And so we have these 2 yields, but this yield is called the theoretical yield. Theoretical yield of product. This yield is an impossible yield. There's no way we can get 315 grams because we just don't have enough oxygen. We're going to run out of oxygen before that happens. And so the oxygen is called the limiting reactant or limiting reagent. Limiting reagent. I should have did this in red. critical yield is based on the limiting reagent. This methane is going to be called the excess reagent. So the yield of CO2, how much CO2 am I going to form from this mixture of 115 grams of methane and 150 grams of O2? Only 103. And I'm going to have some excess methane left over. And so that's going to be one last calculation here. The amount of excess reagent unreacted or left over is equal to the initial amount minus the amount consumed by the LR, limiting reagent. And so the initial amount of methane that I had is 115 grams of methane minus the amount consumed by the limiting reagent. Now, the amount consumed by the limiting reagent, we have to do yet another stoichiometry calculation. So this will be stoichiometry calculation number 3. And so we'll start off with the limiting reagent. The limiting reagent is 150 grams of O2. That's our LR. And so we're going to go from grams of O2 to moles of O2. So a mole of O2 is 32.00 grams. And then from moles of O2, we're going to figure out how many moles of methane. So 150 grams of O2 is going to require or consume how many grams of methane. So what we'll do is we'll go moles of O2 to moles of methane. It's a 1-to-1 mole ratio. And then moles of methane to grams of methane, 16.05 grams of methane per mole of methane. And so this is going to give me the number of grams of methane that were consumed by 150 grams of O2, limiting reagent. So we'll get 115 grams of methane minus, okay, let's do that calculation here. 150 divided by 32 times 1605. 75.23. So only 75.23 grams of methane were actually used out of the 115 grams that we started with. So it looks like we're going to have 39 point, actually we're only allowed one decimal place, so 39.7 grams, or about 40 grams unreacted, 40 grams of methane left over. So what we need is we need more oxygen to burn the remaining 40 grams here. We don't have enough oxygen. That is if I did the calculations correctly. This is like something analogous to this would be like this. Let's do like a bicycle analogy. Bicycle analogy. I'm going to take, let me take 30 pounds of tires. 30 pounds of tires. And 60.3 pounds of frames. So if I take 30 pounds of tires and 60 pounds of frames, how many bicycles can I build? Does that kind of make sense? No, that doesn't really make that much sense because, you know, how much does a tire weigh? Right? How much does a tire weigh? Well, we need to know the mass of a tire. Right? How much does a frame weigh? You need to know that as well. And so that's going to come from the masses. And so what we're going to do is we're going to go from pounds or whatever to the units. So let's say, you know, 30 pounds of tires turns out to be 20 tires. Just like 115 grams of methane turns out to be this many moles of methane. Right? And 60.3 pounds of frames, let's say that turns out to be 30 frames. So from 30 frames, I can figure out how many bikes I can make because each bike needs one frame. So if I have 30 frames, I can build how many bikes? 30 bikes. So I got 30 frames, I'll build 30 bikes. Is that it? I'm done? No, I'm not done because each bike needs 2 tires. If I have 20 tires, how many bikes can I build? If I have 20 tires, I can only build 10 bikes. So what's my theoretical yield of bikes? My theoretical yield of bikes, oh, I know, it's going to be 40 bikes. I can build 40 bikes from this. Is that possible? That's impossible. In fact, could I even build 30 bikes? No, that's an impossible yield. How many bikes can I build? 10 bikes. That's my theoretical yield. My theoretical yield of bikes is 10 because my limiting reagent will be the tires. My excess reagent will be the frames. Now, how many frames will I have left over? Well, the number of frames I'll have left over will be the initial, which is 30, minus the number consumed by the limiting reagent. And so what is the number consumed by the limiting reagent? Well, the limiting reagent is 20 tires, let's say. So if I have 20 tires, then I need 1 frame per tire, and that's going to give me 10 frames.
For 2 tires. What did you mean?
For 2 tires. That's going to give me 10 frames, which is going to give me 20 frames left over. So this is kind of what we're doing here. You know, this limiting reagents. So whenever we're given more than one quantity, then automatically it's a limiting reagent problem. Automatically. We can't assume the other's in excess. If it's not specified, so if I said nothing about the tires, then we'd assume we have plenty of tires, we'd build 30 bikes. If I said nothing about the tires, I would assume. And so, you know, in the previous problem, we were talking about methane, 1 pound of methane. Well, the theoretical yield there is 2.7 because we're going to assume we have plenty of oxygen. Plenty of oxygen, because the oxygen wasn't specified. We can make that assumption that we have plenty of oxygen. And it makes sense because air has plenty of oxygen.
Right there we said 1 mole of O2, and then should it be 1 mole of methane over 1 mole of oxygen, or should it
Right here?
Yeah, it should be 2, right?
I made a mistake, you're right. I made a mistake there. I have to correct it now. Good catch. Yeah, 1 mole of O2. I don't know why I did CO2. I was thinking CO2, but it's wrong. And so let's do the calculation right now as a repeat here. It's going to be 150, actually it's going to just be divided by 2, so what does it come out to? 150 divided by 32 divided by 2 times 1605. 37.61. 37.61. sorry. Correct this. Minus 115. 77.38. 77.38. And so this means 77 grams of methane left over. 77 grams out of the 150. So more than half left over. It's kind of a waste. Okay, is that okay? You guys got it? All right, let's take a break now and then we'll start up again. Break.